Hello, this is Tad Kellogg. I'm going to be presenting today the project using Big Data Hadoop for identification of aberrant behavior clusters in server performance time series data. This is a project for EECS6893 Big Data Analytics, Columbia University. We'll go over some motivation related works to this problem, system overview for the project that facilitates the solving of this problem, and results in future work. The motivation for this particular problem comes from large enterprise data centers or cloud centers that would employ vast numbers of distributed compute servers. It's not uncommon these days for large data centers to have hundreds, if not close to thousands, of physical servers. And with virtualization hybrid techniques, you could have tens of thousands of virtual servers. They all need identification of performance problems, troubleshooting, and that falls into the classification of aberrant behavior, right? Abnormal behavior within the server performance. And a lot of times within these large distributed environments, it's not really clear why a certain server or set of servers might be experiencing abnormal or aberrant behavior. And this project hopes to give a few more tools in that direction, scalable tools, because this is, again, a large problem with large data sets. This particular project is going to look at 2030 physical Linux servers and try and make some identifications of aberrant behavior within that large population. And we're going to do this with a couple of different algorithms. First, let's talk a little bit more about aberrant behavior. Aberrant behavior detection has gone on in, we can see examples within network monitoring, Jake Bootslag's work, and some peer Alexander Mayer did some work with single performance servers. Both had in common the use of the Holtz-Winters algorithm. It's an exponential smoothing algorithm. In weather-related data, it's a triple exponential smoothing. For this particular project, we're going to use the double exponential smoothing version of Holtz-Winters to facilitate creating the confidence bands. That's what you can see in common with both these graphs. The top graph has confidence bands in red. The bottom graph has confidence bands in blue. Holtz-Winter exponential smoothing across the original data is used to create the confidence bands that we can then see if the original data exceeded those confidence bands would indicate abnormal or aberrant behavior. The system is designed in an extract, load, transform methodology. It's consistent with the industry standards for data analytic type platforms. We're going to have an INMON collection that's going to be specific to the organization, however the organization wants to collect INMON data. In this particular example, I have a collection of 90 days worth of 5-minute interval INMON collection for 2,030 servers. That collected data will then be loaded into the Hadoop stack. In this project, my Hadoop stack is simply a single node with 24 cores, 64 gigs of RAM, and 6 terabytes of local storage. It's running the Hortonworks HTTP 2.1 Hadoop stack with Mahout 9.9 libraries. The transform portion of this project will involve using Hive, the data loaded into Hive tables, using Hive streaming with R, and then the Mahout clustering. The Hive streaming with R allows us to run the Holtz-Winter algorithm, producing aberrant percentage points for each server on a particular performance metric, and then we'll use Mahout for libraries for doing the clustering. In this case, k-means is the primary one. INMON data, a little bit about that, because this was the bulk, as most analytic problems and projects go, data wrangling is a big factor in success with a project. And this is where we look at the INMON data, and the data wrangling in this case is to transform this log format into a tabular format for use in Hive. But INMON, like most other time series collection data, is going to proceed in a log-oriented format. The example here shown on the slide is for CPU data. Some of the metrics that collected from the Inmon, which is Nigel's performance monitor. It's an open source package now, originally created at IBM. One interesting thing about this is the big data allows us to do kind of a switch from the industry standard of ETL to ELT, able to do the transform at the end. We're using the Hadoop system because the Hadoop HDFS can take files of any type of format, and we'll use PIG in this case, as I alluded to earlier, to do the transform from log format into tabular format. The PIG transformation is illustrated on this slide, again from the log format over to tabular format. Part of that processing involves such things as joining together date tables or date ranges. Inmon, like most other processing systems, will sometimes view dates in a coded format. The Hive aggregation and streaming are a great example of using Hive for calling external programs and using its internal aggregation metrics or abilities, functions. The max, average, min, the transform and cluster by are used to call R and allows us to use R in a parallel capacity with Hadoop. The Holtz-Winters algorithm is a double exponential smoothing algorithm with baseline and trend coefficients, as you can see in the functions or equations there. We simply use the R function, Holtz-Winters, takes in the data, and gives us back a model to use with that. Using Bertlagg's confidence band formula, we can compute a high confidence band. We're only going to use the high side confidence band in this project, using a weighted average absolute deviation updated with the exponential smoothing gives us that high confidence band twice, as you can see there in the formula. We're going to use that with the metric CPU, active memory, and run queue. And the idea is to look or find the data that went above that high confidence band. That's shown in the graph here as points below the zero line because it's a subtraction from the current data of the high confidence band. So those that are below the line indicate the number of points that occurred within the chart. It's kind of easier to see than just drawing a line. But that gives us a way to calculate a percentage. So in this case, there were 5 data points below the line out of 90 data points. So it gives us a 5% aberrant behavior for this particular server. And we'll use that in the feature vectors, again with the CPU active and run queue. Mahout, the k-means algorithm, fuzzy k-means, rule of thumb equated to about 32 clusters given our 2030 feature vectors. We're using the cosine distance measurement algorithm for similarity measurements. The fuzzy k-means was also used to see if that provided any performance improvement in clustering. The feature vectors were formulated with the ARFF dot vector algorithm within Mahout, which uses the it's really a CVS format with prepended data instructions, and the examples there shown on the screen. Cluster dump evaluate option was used to compute the intercluster distances, the intracluster distances, and also giving us a GraphML output of the cluster, so we could use the iGraph package within R to generate some charts. The results, the main successful contribution was the ELT software infrastructure methodology, basically the data wrangling of this project for big data implementation with Hadoop. Released open source in the GitHub archive there. The PIG transform of the Inmon data into Hive tables, using the Hive tables with R and Mahout integration, and having a scalable solution for this aberrant behavior detection with 2,030 servers. We can crunch through and get out the aberrant behavior percentages, feature vectors, in really reasonable time with our simple test machine. And we can see that we reduce the time by increasing the number of reducers by 2. Memory constraints could not go higher than that in this particular test. But if we do a simple exponential smoothing of the 2 or trend line of the 2 data points, we can see that we should be able to at least increase to 28 cores and have some more scalability. So good results there for scalability. And aberrant behavior detection. The clustering, some possible good results, as we can see from the charting and from the cluster distances. Didn't see a lot of good intra-cluster distances that we'd like to, not a lot of separation between the clusters, so you end up with a huge clump of clusters around a common centroid. The 32 cluster, though, and above had similar chart showings and similar sizes, as we can see in the cluster distances table. The interesting thing about this is those outlier systems, the outlier points indicate servers that could be worth investigation. Their aberrant behavior somehow didn't fit the rest of the pattern with the majority of servers, right, the large majority. So that indicates a good potential jump-off point for investigation and use of this particular algorithm and project. Future work, add additional aberrant server performance metrics, add I/O statistics, some networking statistics to the feature vectors. That may get us some better cluster distances, some better cluster formations. Seasonal coefficients the whole winter, triple exponential smoothing. If we have the data, I would like to see above 6 months worth of data to a year before that's implemented. And increase the Hadoop cluster resources to verify our scalability with this solution. Add some more points to that line and see really where our scalability can go with additional Hadoop cluster resources. And of course, changing the cluster algorithm, perhaps using spectral or streaming k-means, might give some better cluster results, or more interesting ones at least, as this is an unsupervised learning discovery on the cluster side. Thank you for your time, and thank you to Dr. Lin and Columbia University.